All right, if there's no questions, let's kind of direct our attention to the topic that we were discussing at the end of class on Monday, and that is prime and maximal ideals. So remember, the definition of a prime ideal is if you have a product of any two terms that are in the ideal, at least one of the two factors has to be in the ideal. So we showed that the principal ideal generated by 6 in Z, that is not a prime ideal because the product 2 times 3 is 6, which is in the ideal, but neither 2 nor 3 are elements. In fact, we'd have to have one of the two be in the ideal for it to be prime. So it is not prime because not every product of two elements from the ring has at least one of those elements in the ideal. We talked about whether or not the principal ideal 6 was maximal, and we said no, because clearly the set of all multiples of 6 in the integers is a subset of all multiples of 2. So to be a maximal ideal, you can't be a subset of any other ideal except the entire ring itself. So this is not a maximal ideal. And it turns out that in the integers, the maximal ideals are all of the principal ideals generated by prime numbers. The prime ideals are exactly the same, with the exception of also including 0. 0, the ideal generated by 0 is always a prime ideal. And because all of the maximal ideals in the integers are principal ideals, then Z is a special kind of structure called a principal ideal domain, or PID. So this is what maximal and prime ideals look like in the integers. Let's do a similar example now for the integers mod n and see if we can come up with a similar sort of conclusion. So let's talk about what are the maximal ideals of Z24, what are the prime ideals, and then see if we can generalize that to Z mod n. So I'm just going to start listing off what are the ideals of Z24, any ideal, not thinking about prime or maximal or anything like that. What are the ideals of Z24? So the ideals of Z24 are, obviously 0, which is just the 0 element. If you have the ideal generated by 1, then that's all of Z24, right? So the ideal generated by the element 1, that's all of Z24. Those are kind of the trivial cases. What about the ideal generated by 2? Well, the ideal generated by 2, that's all of the even elements. Clearly, that contains the ideal generated by 4 and the ideal generated by 8. Those are all contained in the ideal generated by 2. So these are all, we can write down what those elements are, but it would be 2 times an element from Z24, right? So, you've got all of the even integers in Z24, all the multiples of 4 in Z24, all the multiples of 8, and so on. If you were to do this again for 3 contains all of the multiples of 6, which contains all of the multiples of 12. And it turns out that if you try any other generator, then it's equivalent to one of these, right? Or it doesn't actually form an ideal. So all of the other principal ideals that we might come up with are one of these 8, it turns out. If you are relatively prime to 24, you're going to generate the entire ideal, right? So the ideal generated by 5 is the same as the ideal generated by 1. So we have this sort of structure which lends itself really well to creating what's called an ideal lattice, which is similar to a subgroup lattice that we might have talked about when we were doing groups. But the ideal lattice for Z24 looks like this. You start at the bottom with the 0 ideal. Then the 2 smallest ideals above that, this is the smallest ideal. The next smallest are the multiples of 8 and the multiples of 12. There are only 2 elements in the principal ideal generated by 12. It's the element 0 and 12. principal ideal generated by 8, it's 0, 8, and 16. So you've got 12 as one of them, and then you've got 8 as another. Okay, if you go beyond that, then you've got 4 and 6 are kind of at the next level. So let me just draw in 4 and 6. And what we will typically do is if they are subsetted, like 8 is a subset of 4, then you'll draw a line to it. Here, 12 is also a subset of 4, though, right? All the multiples of 12, that is a subset of the multiples of 4. So I actually am going to draw this here to show that they're connected. And then, of course, 12, the principal ideal generated by 12 is a subset of the principal ideal generated by 6. So multiples of 12 are a subset of multiples of 6. If we keep going, then the next level is going to have 2 and 3. And 2 and 3, we get the direct subset inclusions there. But then 6 is also going to be a subset of 2. Finally, at the very top of this lattice is the principal ideal generated by 1, which is all of Z24. And we have this sort of inclusion there. So this would be what we call the ideal lattice for Z24. It's a way of showing the structure and what the subset inclusions are. From this ideal lattice, you can immediately make a couple of observations. First, D is an ideal of Z mod N if and only if what's true. D divides N. And what I mean by that is these are the non-trivial ideals, right? So the non-trivial ideals, the ones here in the middle, including 0, I suppose, are the elements for which D divides N. So that's how you get an ideal, non-trivial ideal in Z mod N. Taking it a step further, the maximal ideals of Z mod N, if and only if you're of the form P, where P divides N is prime. So the maximal ideals of Z mod N are the elements, the ideal generated by 2 and the ideal generated by 3. They're at the top of this ideal chain. They're the maximum ones. The only ideals which contain them are the entire ideal, the entire ring Z24. So this is slightly different than in the integers, because in the integers, to be a maximal ideal, all you had to do was be an ideal generated by prime. But here you have to be generated by a prime that divides 24, meaning it's a prime factor of N, right? So the prime factors of N are the maximal ideals in Z mod N. And taking that, a step further, the prime ideals of Z mod N are precisely the maximal ideals plus the 0 ideal. So because of this, the structure is very similar in terms of ideals for Z mod N as it is for Z, the integers. So Z mod N is also a principal ideal domain because all of its maximal ideals are principal ideals. There are no non-principal ideals in the integers mod N. So this example, while specific, is typical of all Z mod N examples. So it should be relatively easy for you to pick out what are the prime and maximal ideals if we're talking about the integers or the integers modulo N. All right. So we discussed last time that this factor group we think is isomorphic to a copy of the complex numbers. Because the complex numbers are a field, we're going to show here in just a second that that implies that this ideal generated by the polynomial x squared plus 1 has to be maximal. But we're not there yet. I haven't shown you the theorem that talks about that. That's the R mod I or R mod A theorem, where A is a maximal. So we haven't talked about that theorem just yet, but I still want to show that this ideal is maximal. So this is an example of how to prove that a given ideal is maximal. And so what we're going to do here is we're going to assume, this is how you should always do a proof of a maximal ideal. We're going to assume that A is a maximal, is an ideal of the ring R over R of X, the ring of polynomials over the reals, that contains the principal ideal generated by x squared plus 1. What we're going to end up showing, so we want to show that that ideal turns out to be the entire ring because it will contain a constant. Now, why is that enough to conclude that the ideal, if I can show that this ideal A, which contains my principal ideal, if I can show that that ideal A contains a constant, why is that enough to prove that it's the entire ring? As soon as I know that this ideal contains a constant, why do I know it's the entire ring?
You can go from a constant to x squared, or a...
Okay, kind of, yeah. I think you're thinking about Monday's talk where we were talking about this, and I think there's an argument to be made there along the lines of what you're saying. But I'm actually thinking even simpler. Ideals absorb, right? So if C is an element of A, then C times 1 over C must also be an element of A. And the reason for that is since R of X is a field, right? Since the reals form a field, as soon as I get a constant polynomial in A, then I get its inverse polynomial in A, which is 1 over C. But because it's an ideal, it absorbs, right? So whatever this product is has to get absorbed into A, and that product is 1. So as soon as the identity polynomial 1 gets into the ideal, then because of absorption, it absorbs every other element of the ring into the ideal because they all get multiplied by 1. So in a field, as soon as you get a constant into an ideal of a field, you generate the entire field. That's kind of an important point to remember kind of moving forward here. So if a constant is in the ideal, then so is the product of it with its inverse, which turns out to be 1, which implies that A would then equal the entire ring. So that's what we're going for to prove this, is we're trying to prove that this ideal will contain a constant. So we're going to do this in steps. So step 1, we're going to say, suppose that you've got a polynomial that exists in this, supposed containing ideal, but that polynomial is not in the principal ideal. So it's somewhere in between the two. Then if that's the case, that polynomial must be of the form f of x equal to q of x times x squared plus 1 plus r of x, where r of x is not 0 and the degree of r of x is less than 2. So this is the line that's going to need the most explanation, I think. This is reminiscent of what that we talked about early in the course. What does this remind you of? Yeah, it reminds you of the division algorithm, right? So this should remind you of the division algorithm. You have a division algorithm for polynomials just like you have it for integers. In particular, what we're looking at is we're looking at the mod x squared plus 1 representation of f of x. So I know I can write f of x in terms of any other polynomials. I'm choosing to write it in terms of x squared plus 1 because the principal ideal generated by x squared plus 1 is important for this problem. I know that the remainder can't be 0 because if the remainder is 0, then f of x is a multiple of x squared plus 1, which puts it in this principal ideal, but I just assumed it wasn't in that principal ideal. So I know I have to have a non-zero remainder, and I know the remainder has to have a degree less than the divisor. So the divisor here is x squared plus 1, so I know the remainder has to have degree less than 2. So the fallout from that is that the remainder must be linear or constant. So it must be of this form. Well, if it's of that form, then I can rewrite this expression in terms of r of x. So if I solve this expression for r of x, I get that r of x is f of x minus q of x times x squared plus 1. And f of x is an element of A, and q of x times x squared plus 1 is an element of the principal ideal, but A contains that principal ideal. So this is an element of A. This product is also an element of A. And since A is an ideal, it's closed under subtraction. So I know subtracting those two polynomials will put this thing in A. So I know that whatever the remainder is, I know it's an element of A. That's important because it tells me the following. If I was to look at a squared x squared minus b, and I know that's coming out of nowhere, but what that is it's ax plus b times ax minus b. This quantity must be in the ideal as well, because I just showed that ax plus b is in the ideal. So it absorbs anything from the ring. So ax plus b times any element from the ring is in A. In particular, ax plus b times ax minus b must be in A because of absorption. So what constant is it? Remember, we're trying to find a constant that belongs to A. What constant is it that I'm going to look at? Well, it needs to be non-zero. And it turns out that it is a squared plus b squared. This constant must be in A because this is a squared x squared plus a squared minus a squared x squared minus b squared. Those were clearly chosen secretively, so that, or intentionally, I might add, so that we knew these were elements of A, right? So this is an element of A. We just showed that on the previous line. Oh, sorry, that should be b squared there. We just showed that on the previous line. And then here, this is the same thing as a squared x squared plus 1, which means it's in this principal ideal, which means since A contains it, this thing is in A. So I have two elements of A subtracted, which means their subtraction or their difference is in A as well. So this is the constant C that I talked about at the beginning. And as soon as that constant C is in the ideal, then I know that it generates the entire ring. So why is this a proof that this principal ideal is maximal? Why does this prove it? Well, it proves it because the definition of a maximal ideal is the only ideal which contains it properly is the entire ring. So we assumed that I had an ideal that contained it properly. And we showed that if that's the case, then that ideal must be the entire ring. So the conclusion down here at the bottom is that A must be the entire ring. So x squared plus 1 is maximal. Now, I don't know about you, but to me, that's a little bit of a headache to have to go through every time I want to prove that an ideal is maximal. So we're going to have a better way of proving that a given ideal is maximal here in just a little bit. But this is what a proof without this additional information that I'm going to give you here in a little bit. This is what a proof of proving that something's maximal would look like. All right. So next example up, how do you prove that something is prime? So I want to show that this principal ideal generated by x is prime in the integers, in the polynomials with integer coefficients ring. So in order to do that, to show that it's prime, I have to look at all possible products that end up in it and show one of the two factors is in it. So keep in mind that this is the set of all f of x well, how about do it this way? It's the set of all things of the form x times f of x such that f of x is in z of x. And we've actually run into this ideal before in a previous lecture. We said that this is really just the same thing as all f of x in z of x, where f at 0 is 0. So if the principal ideal generated by x multiplies every polynomial by x. So if you multiply a polynomial by x, you multiply the constant term by x, which means you have a 0 constant term. So these are all the polynomials with 0 constant term. So let's talk about prime, right? So how would you prove or disprove that this thing is prime? Well, the idea is, suppose that you have two functions that when multiplied end up in this ideal, right? And this is where g of x and h of x are elements from the ring. Then because they ended up in the ideal, they must have a constant term, which is 0. Then g of 0, h of 0 must be equal to 0. But since g of 0 is an integer, and h of 0 is also an integer because they're the constant term of a polynomial. Since these are both integers, what can we say about the product of two things giving 0 in the integers? The integers are an integral domain, right? So we've looked at that before. Since the integers are an integral domain, that means they have no 0 divisors. So if you have a product of two integers that's 0, then like Wyatt put in chat, one of them must be 0. So since g of 0 and h of 0 are integers, then either g of 0 is 0 or h of 0 is 0. In either case, g of x or h of x is an element of this principal ideal. There's no way that one of these isn't in the principal ideal because one of them has to have a 0 constant term. So the conclusion there is that this is a prime ideal. So proving that things are prime is not terrible, usually. Maximal here is pretty trivial because we've already looked at a ring together that can, or an ideal together that contains this one. What ideal that we've discussed properly contains this one? We talked about the set of all polynomials with even coefficients, or even constant term, excuse me. And that was generated by this ideal. So if you look back at the notes from earlier in the week, that ideal is the ideal consisting of all polynomials with even constant terms. Since 0 is an even constant term, then this ideal necessarily contains the ideal we just looked at. So it can't be maximal. So Wyatt's question is, could we also prove something is prime by taking arbitrary elements from Zx that both aren't in X and showing that the product isn't in X? Let me think about that. Taking that both aren't in X. Yes. So you would be saying that a product outside of let me think about that. A product, you would be saying that a product with factors outside the ideal never end up in the ideal. That means that if you have a product that is in the ideal, so if the factors start outside the ideal, then the product lines up in the ideal. So if the product doesn't wind up in the ideal, then the factors didn't start outside the ideal. At least one of the factors is in the ideal. Yes, that's the contrapositive. That would work. Because basically you're proving the contrapositive of the definition of prime. The definition of prime is if f of x times g of x is in the ideal, then f of x or g of x is in the ideal, right? Then either one of those is in the ideal. The contrapositive to that statement, so this is the original statement, the contrapositive is if neither f of x or g of x is in A, meaning they're outside the ideal, then f of x, g of x is not in A. Yeah, so you can also prove primality by showing that a product of any two things outside the ideal never winds up in the ideal. Yeah, a product of any two things outside the ideal never winds up in the ideal. That would work just fine. Okay, that brings us to our final two theorems, and I probably don't have time to prove these, okay? The proofs are not difficult. They are in the textbook and they are in the notes that I put online. But I do want to talk about the ramifications of these. So both of these proofs that we just did, the proof that this is maximal and the proof that this is primal or prime. I always say primal, the proof that this is prime. Those proofs are pretty direct and pretty straightforward, although they can be complicated to prove that a given ideal is prime or maximal. Instead, oftentimes what you want to do is form the factor ring. So if you're given an ideal and asked to prove whether it's prime or maximal, take and form the factor ring that that ideal creates with the ring that contains it. And then if you can prove that that factor ring is an integral domain, you automatically know the ideal is prime. You don't have to prove anything about primeness. You get that for free. So if the factor ring is an integral domain, then the ideal that generated it is prime. That is a big result. You should be using that result to help you prove some things this week and some stuff that's going to show up on Module 9 homework as well. And then here is the same thing, but if it happens to end up being a field, so if you form the factor ring and it ends up being a field, then you know that the ideal that you're modding out by is a maximal ideal. So if R mod A is an integral domain, A is prime. If R mod A is a field, A is maximal. And I know you had to memorize those for your definition and terminology quiz on Monday, but they are really important results that can save you a ton of effort. So I want you to be thinking about these two results often when you're asked to prove things about prime or maximal ideals. This is usually a much more efficient path to proving those statements. All right, sorry we don't have enough time to go over the proofs, but I do encourage you to look at the proofs. The proofs are there in the work. All right, that leaves us 15 minutes. I want to devote that time to looking at the skills quiz with you. And then that'll leave us Friday to cover ring homomorphisms and the first isomorphism theorem for rings, which will take us the class. We shouldn't be over time on that. And the notes for that are already up, by the way. So if you want to get a head start looking at those to study for, the notes for that Friday class are already up and out there for you. All right, let's take a look at the skills quiz together. And if you'll upload it later today, I'll take a look at what you got. All right, so we're going to start with this was kind of a little mini proof here, asking, are the Gaussian integers, is the set of Gaussian integers with even coefficients, is that a subring of the Gaussian integers? Is it an ideal? So I've got to check three things here. I've got to check subtraction, multiplication, and absorption. It is closed under subtraction. That's pretty easy to show. It's closed under multiplication. That's also easy to show. However, it's not closed under absorption because if you look here, it's very important that you know, for example, that when you do the product A times D, you need to know that that's even. If you don't know, for example, that D is even, then A times D will be even, B times C will be even, because you know at least one of them is coming from there, but you don't know that both of them is coming from there. And so if you don't know that both of them are coming from there, then you can end up with some odd products. And so an example of that here is if you take 1 plus 2i and multiply it by 1 plus I, then you don't get absorption there when B is even. It's just B, it's not A, right? A can be anything. But if only one of the two has a imaginary term that's even, then you can end up with a product where the imaginary term is not even. So it does not absorb. So give yourself half a point if you felt like you did the subring part correctly and you didn't do the absorption correctly, or vice versa. But 1 point for that question. All right, we're looking at all of the prime ideals for this direct product of Z8 and Z30. So, you know, we just got through here in the lecture talking about what are the prime ideals, what are the maximal ideals of Z mod N. So we know that the prime ideals are the 0 ideal together with any of the prime factors of 8. So the prime factors of 8 are 2. So I can pair that up with 0 and get a prime ideal. I can also generate the entire ring. So the prime ideals turn out to be, for Z8, you can have 1, 0, or 2. For Z30, it turns out that you can have 2, 3, or 5, or you can have 1, or you can have 0. So these are the prime ideals of this ring. So let's do half point for each of these, and then 1 point for the conclusion. So half point for A, half point for B, and then a half point or 1 point for the conclusion. So the maximal ideals of R are the ones that aren't, so you're looking at all of these, find the ones that aren't contained by any of the others. Why is 2 plus 2 not prime? So 2 plus 2. So if you're generating 2, that would be 0, 2, 4, 6. This would be 0, 2, 4, all the way up to 28. And if it were prime, then if you took something like 2, 2, no, that can't be in there. If you took something like 2, 3, and three, 2, then you would get 6, 6, which is in this, but neither of those is in that. Does that make sense? So yeah, it can be really difficult to tell which ones are prime and which ones aren't. I completely agree. The prime question is far harder than the maximal question is. So this is a reason why 2 plus 2, it's not as simple as just listing all the prime ideals of each one and combining them, because you have to especially be careful when it's the same ideal on both sides. That's usually the case where things go wrong. If they share a prime factor, that's when you need to be concerned. So to Wyatt's question here, like one of the things you need to really watch out for are any prime factors that they share. They both share a prime factor of 2. I believe that's it. Yeah. If they were to both share a prime factor of 3, then you would need to be really suspicious of 3 plus 3, the prime ideals there. And so these are the maximal ideals, because each of these is maximal in their respective group. That one's much easier to pull together. You can always pair it up with a copy of 1, which is the entire ring, and then the other piece having a subcopy. You still can't do, even though 2 is maximal in both Z8 and Z30, you can't do 2 plus 2 for the reason I mentioned here, because it won't be prime. So these are the only maximal ideals on part B. So no 2 and 2 on that one as well. And so, you know, this one is probably going to mess you up. If you messed up on A, it's probably going to mess you up on B and C as well. You're probably going to have this 2, 2 all the way through. So for each maximal ideal, define and identify the size. Basically, we're just going to mod out by this and see how many elements are in it. This one has, what, 240 elements. 1 generates all of Z8, so that's 8 elements. This generates half of Z30, so that's half of 30. So you literally get half as many here as here. So it's a total of 2 elements in that ring. So it's isomorphic to Z2. Same thing here, because you're just flipping it. So you're getting half of this ring back, all of this ring back. So all totaled, you're half the ideal that generates it is half of the entire ring. So this has size 2 as well. Over here, this is a third of it. So you're going to have 3. The principal ideal generated by 5 is a fifth of the size of Z30. So it's going to have a total size of 5. So that's isomorphic to Z5. And so here's the big sort of light bulb moment, if you will. All 4 of these are fields. Z2, Z3, Z5, they're all fields. And so we get this factor ring modded out by a maximal ideal forms a ring, or forms a field, excuse me. So I know that these are maximal ideals because of the number of elements that are in the set of all cosets form, the factor ring. All right, on to number 3. I want to show that this thing is a maximal ideal. What happens if 3x is replaced by 4x? Then generalize. So the set Z cross Z mod A consists of 0, 0, 1, 0, 2, 0. And the reason that it consists of those 3 things is because you're looking at multiples of 3 in this first slot. So all you really care about is, are you 3x plus 0, 3x plus 1, or 3x plus 2? Because everything else gets absorbed back into 3x. So up, as distinct as we can make it, these are the 3 elements that are in this factor ring. So this is going to be isomorphic to Z3, which is a field. So that implies that A is maximal. So this is where that R mod A theorem really comes in handy. I know that since this forms a field, that this will be maximal. And you can clearly see, I'm not using a theorem to tell me that this is isomorphic to Z3. You can just clearly see that there's a mapping from the elements 0, 1, 2, mod 3 onto the elements that are in this coset. It's just clear that this is Z mod 3. If I do the same thing with 4x, then we get this structure right here. But this structure is not a field because it would be isomorphic to Z4. And we know that Z4 doesn't form a field. For instance, what is the inverse, the multiplicative inverse of the element 2, 0? It doesn't have one. So this element is not a unit, which means this thing is not a field. So the generalization of this is, if you're looking at the ideal generated by a multiple of x in one slot and then just an integer in the other slot, it's only maximal if this integer n is prime. That's the only way it's going to be maximal. And if it is, then the factor ring is going to be isomorphic to Z mod n in that case. Okay. So on to number 4. In the ring of integers, in the ring of polynomials over the integers modulo 5, mod this ideal. What is the multiplicative inverse of this coset? So what I'm really asking is, can I take another element that's of the form ax plus b and show that I get 1 plus I? And I know that if you think about it for a little bit, you know, based on what we've talked about in class, that all of the elements of this factor ring are going to be linear functions or degree 1 or lower polynomials. So if this were true, then that's like saying 2x plus 3 times ax plus b needs to be equivalent to 1, right? The representatives multiplied together need to give me 1 mod 5. So I FOILed all that out. I then combined like terms. So I have this expression here. But I know that since I'm in the ideal x squared plus x plus 2, that x squared plus x plus 2 gets mapped to 0 in that ideal, which means that x squared plus x plus 3, I added 1 to both sides, is equivalent to 1. And the reason that I bring that up is I know that if I have a polynomial that's equivalent to 1, then the constant term has to be 3. So if the constant term has to be 3, then I need 3b to be equivalent to 1, which means that b is equivalent to 1, because the constant term here needs to be equivalent to the constant term here. I also know that 2a here needs to be equivalent to 1 here, so that what I'm working with there would lead me to believe that a is 3. So this was my thinking. There are different ways to do this problem. This was just kind of my thinking here. But it does turn out that I did find the correct inverse. So 3x plus 1 is the inverse of 2x plus 3 in this factoring. Yeah, so there's different ways to do that, but 3x plus 1 is the answer there. You could have also done it by trial and error. I mean, there's just not that many combinations to kind of work through there. So trial and error would have worked as well. And so that's worth 1 point for that problem. All right, now this gets me to the heart of this skills quiz. You really need to be able to do problem number 5, okay? I think we actually looked at A in class, if I'm not mistaken, so hopefully none of you missed A. If you look at 3 plus I times 3 minus I, you get 10. So that's equivalent to saying that 10, because 3 plus I times 3 minus I is absorbed into the ideal, then so is 10. So 10 gets mapped to 0. You could also say this says 3 plus I is equivalent to 0, so I is equivalent to -3, which makes I equivalent to 7 because you're just adding 10 there. There are lots of different ways to do this. The point is you wind up with 10 elements and you think this thing is going to be isomorphic to Z mod 10. It is isomorphic to Z mod 10. So this guy right here is isomorphic to Z mod 10. There are 10 elements in that factoring. On B, this one's a little trickier because you've got 2 generators here. So you know the ideal is generated by 3 times some function plus x squared plus 1 times another function. So this is true for any f and g and z. So the immediate things that I can look at is what if g is 0 and f is 1? Then that says 3 is in this ideal. Well, if 3 is in the ideal, then 3 maps to 0. And that immediately gives me a mod 3 structure. Well, I also know the other generator is in the ideal. So if the other generator is in the ideal, then x squared plus 1 being in the ideal being mapped to 0 means x squared is equivalent to -1. So I can reduce all polynomials to degree 1 polynomials because everything degree 2 or higher gets reduced to a constant. So because of that, and because I'm looking at all linear polynomials where the coefficients are mod 3, then I know these are the possibilities. So these are all of the possible linear polynomials whose coefficients are equivalent or come from the integers mod 3. So that's what this thing would be. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9 total elements. It remains to be seen whether that is isomorphic to Z mod 9 or Z3 cross Z3 or some other field of some other ring of 9 elements. Luckily, we weren't asked to that here, but there are in fact 9 elements there. On C, 2 plus 2i gets zeroed out, so 2i is equivalent to -2. Which the other thing to recognize here is that if you take 2 plus 2i times 2 minus 2i, if you do the conjugate multiplication here, you get 8. So 8 is also absorbed by the ideal. So 8 maps to 0, which means I can add 8 and get that I is equivalent to 3 ultimately here. So using these sorts of substitutions, like we talked about in class on Monday, I can reduce this thing down to where it's just a constant. So all of the representatives are a constant, but they're all equivalent mod 8. So this is just a copy of Z mod 8. There are 8 elements here. Finally, the last one, which is the hardest one here on the skills quiz, in my opinion. You're looking at all these different equivalences, right? So you've got 1 plus I. 1 plus I is equivalent to 0. So I is equivalent to -1. That's pretty easy. But you can also take 1 plus I and multiply it by 1 minus I. And as soon as you do that, you're going to get, what is that, 2? So you know 2 is equivalent to 0 mod I. So as soon as you start messing around, what you notice is it looks like you've got all of these, but you just start doing some work and everything's equivalent to everything in this ring. So once you start making all of those equivalences pop out, it's not just Z5 that comes about here. You can actually show 1 is equivalent to 0, 2 is equivalent to 0, like we just did. And once you have those, then you get all of them are equivalent to all of them. So I would think that for a student working on D for the first time, most of you probably put down it either had 2 elements or it had 5 elements. That's just a guess, but that's what I think a lot of students working on that problem for the first time would put. Definitely give yourself half credit if that's what you put. But it turns out that all of these are equivalent to one another. And so there's really only one element in this factor ring. This is actually the 0 ring in disguise. All right, that was a tricky one there at the end. So shouldn't the -2 be a 2 and not a 6? Right here. 2 plus 2i. So shouldn't the -2 be a 2? 2 plus 2i times 1 minus I is equal to 1. Wyatt, that's not equal to 4. Oh, well, unless you're reducing it by 3. Let me see. 2i minus 2i cancels. Minus 2i squared. 2. Oh, it is 4. Never mind. That is 4. So you're saying 4 is equivalent to 0. So 2i is equivalent to 2. I is equivalent to 3. Okay. So you're saying that C further reduces? Did I miss that one? So you ended up with 4 elements. 2 plus 2i times 1 minus I. Minus I, 1 minus I, so it would have to absorb it. Yeah, I agree with you. The 4 makes sense there. Yeah, I think you're probably right. I think I did mess that one up. I'll rework it and upload it. I think the answer there is 4. I think you're right. I'll rework it and upload it for y'all. But if on C that you got 4 elements, I do believe that is correct. There would be 4 elements there. It would be equivalent mod 4 is what you'd be able to show. Yeah, good catch. Good catch. All right, sorry that went a little bit over. I knew it would take us a while to get through this particular skills quiz. You're definitely going to have questions like number 5 on this exam. It's a really important skill. Make sure you go back and take a look at those. All right, y'all stay safe. Hope everybody's doing well. I will have the definition terminology quiz ready for us on Friday. Janae, if you want to count it correct, if you want to count it If you want to count it, that's fine. If you put 8, because I messed it up too. I'm going to take a look at it though, just to make sure. All right. See y'all back on Friday.